and about the barium star phenomenon to be or not to be.
Second one. Yeah, that one. Yeah. Yeah. Hi, everyone. My name is Anna. I'm doing my PhD in Belgium in a collaboration program between the KU Leuven and the ULB. And as Sophie said, my PhD project is about barium stars. We are trying to understand their formation and evolution better. And I am going to show you today the observational effort that we have been doing during these 2 years towards this goal. Let me first remind you what barium stars are, although they have been mentioned already a couple of times today. These stars are giants that show overabundances of barium and other S-process elements on their surface, but which are not evolved enough to have produced these elements themselves, because the S-process elements are the product of the slow neutron capture process of nucleosynthesis, which takes place here in the AGB phase, and barium stars are found in the giant phase or even at earlier evolutionary phases. Ono Pols already explained the formation scenario of these objects. They are the second star evolving in a lower intermediate mass binary system, in which the more massive star reached the AGB phase, synthesized the S-process elements, and polluted the companion. So we are observing the polluted companion of these AGB stars, and the pollution could happen through wind or roach overflow, as Ono has already explained. As he also said, the formation scenario is not as clear as it seems. There are still a lot of uncertainties. We don't know the initial parameters of these binary systems that will lead to the formation of a barium star. We also don't understand the mass transfer scenario, and as it has been shown already, this has a strong impact on the evolution of the orbit. So we are not able, our evolutionary models are not able to reproduce the orbital elements that we observe for these objects. And we also don't totally understand the evolutionary links between the progenitors of these stars. So the goal of my research, as I said, is improving our understanding of these objects. And we are going to do this by comparing observational and theoretical HR and ELOC-P diagram in order to put constraints on evolutionary models that will teach us about the evolution and interaction in low and intermediate mass binary systems. And the reason why we want to do this through the study of barium stars is because they are all known to be formed in this way. They are all giant or main sequence stars with white dwarf companion that got polluted during the AGB phase with AGB products. And then we have together the dynamical constraints and the chemical constraints to put constraints in our evolutionary models. I am going to talk about the observational work up until now. And we have been focusing on this because it's the right time to try to build an HR diagram, thanks to the first data released of the Gaia satellite. And also because I am in the right place to try to build an eccentricity period diagram, because the KU Leuven and the ULB, together with other partner institutes, have a high-resolution spectrograph that has been monitoring white binaries for a long time already. Because I didn't mention, but Ono did, these binaries have really long periods. So to actually constrain the orbital parameters, we need long monitoring programs. So let me show you the HR diagram. I'm going to focus on that. I will only mention the ELOC-P diagram at the very end. And we have built this HR diagram using the parallaxes of the Tycho Gaia astrometric solution. And this is how we selected our objects. We went to all catalogs of barium and related stars and took from those all the stars with Tycho, which were part also of the Tycho 2 catalog, because we knew that TGAS was only going to include these objects. And at this point, we had about 550 objects. When the data release took place, we queried the TGAS catalog, and we discovered that we only had 400 objects there, and still applied a quality condition for the parallax and took only objects with parallax higher than 3 times the error bar, which are these objects to the right of this red line. And at this point, we had 323 objects, all of them barium star or stars formed in the same way. And we were curious why we lost so many objects already before the data release. And the reason is that some of them were too bright to be part of Gaia. And we applied the same quality condition over the Hipparcos parallax and still rescue more than 100 objects in this way. and we build the HR diagram for these objects. So to build an HR diagram, we want temperature and luminosity, and we obtain these parameters by fitting a spectral energy distribution. We retrieve available photometry in the literature. Here you have an example of one of our SEDs, and we apply a chi-square minimization method to over a grid of Mark models atmospheres to find the stellar parameters. This is how the same SED looks fitted. We had these four free parameters, and here you can see the chi-square plots, the 2D chi-square plots to see how these elements are entangled. And we decided that 4 free parameters were too many for an SED, and decided to apply some constraints to some of them. We use galactic extinction maps to constrain the reddening, because as you can see here, strongly correlates with the temperature. So applying constraints on this parameter will help us get a better temperature estimation. And we also fix the metallicity of the Mark model atmospheres to minus 0.25, because I will show you later the distribution of the known metallicities of barium stars found in the literature, but the range is not so wide and peaks at about this value. So we consider that using this metallicity was going to help us. And this is how the HR diagram of the barium stars looks like. I am going to stop a minute here to answer your question before. The other day, on Thursday, we had the idea that the time that these dwarfs had needed to reach that point from the 0H main sequence will give us a clue about the time that the companion needed to travel the whole way through the AGB and cooling. And we did some rough numbers, Thursday, 6 p.m., and we obtained that these 2 solar mass stars needed a companion, so a former primary of 2 solar mass stars or less to reach this point. So this is very model dependent, so I cannot tell you more, but yeah, this might be a clue that these stars appear bluer than they should be due to mass transfer. So apart from this, obvious conclusion already by looking at the HR diagram, the historically named subgiant CH star occupy the same region that the dwarf barium stars, so probably this subgiant dwarf differentiation shouldn't be taken too seriously. We also find objects at higher masses, like too high to be the second star evolving in a low and intermediate mass binary system. I will talk about those later. And we also find a strong correlation of barium stars in the clump. I didn't mention before, probably Ono did, these CH stars are the low metallicity counterparts of barium stars. So stars formed polluted in the same way, but with lower metallicity. So what can we learn from this HR diagram? We determined the mass distribution of these objects. We created a grid interpolating between the star-evolved evolutionary tracks, and each point of the grid was characterized by a temperature, luminosity, and a mass. And we associated to each star a mass and created the mass distribution. We took into account the time that the star spends at different evolutionary phases in a way that longer evolutionary phases will have more points in the grid. And this is what we obtained. The black distribution is the one that we obtained with the points on the HR diagram. The red and the green are the ones associated to taking into account the plus and minus error bar. And we conclude from here that the uncertainties are still play an important role to determine the mass of these stars, although we see a clear peak at about 2.5 solar masses, which is slightly more massive than what was expected. But yeah, we think that temperatures determined by spectroscopy and further future data released of Gaia will reduce this problem. We wanted to study the effect that our choice of the metallicity had on these results, and we repeated the process for 2 other different metallicities. Here is the distribution of the metallicities for barium stars that we found in the literature, which made us choose that minus 0.5 as a main result to fix our Mark's model atmospheres. And we see that the peak shifts with the metallicity, and this is because there is a strong degeneracy between the metallicity and the mass at this point where our barium stars clump. So the conclusion of this is that, again, spectroscopically determined metallicities are important if we want to give results about concrete objects. But the bright side of this is that we found already a lot of data available in the literature, and that we have a strong high-resolution spectrograph at our disposal to do that as well. We also tried to compare these results with the mass distributions of giants, single red giants. We find, so here the black distribution is the same one that I showed you before, the 1,4 minus 0.5 of our barium giants. I didn't mention, but we are including here only barium giants. We forgot about the dwarfs and about the CH stars. The CH stars, because of metallicity issues, they are known to have lower metallicity, and the dwarf because the sample is biased towards lower mass stars. So we are using here only the barium giants. This is the black one is the distribution of these stars, and the red one is the distribution that we obtain for a sample of about 3,000 red giants, single red giants. The peak seems to appear at the similar masses, which is just correlated to the accumulation of giants in the clamp, so probably due just to evolution of giant stars. We find deficit here of low mass barium stars. We think that this probably never formed because a lower mass barium star probably had a lower mass primary companion, which had a larger radii already when going through the RGB phase. So probably the tidal interaction was too strong already when the first star was evolving and the pollution never happened. And here we observed also an excess of barium stars at higher masses. And we think that this is due to a pollution of the sample, and I'm going to show you that in a minute as well. But first I have to mention the barium index. This is a way that was used before to classify barium stars, so using the visual inspection of the strength of the spectral line. And it goes from BA1 to barium 5, being barium 5 the more enhanced, or the one with the stronger line. And for example, we find that also stars with indexes 1 to 2 have historically been called mild barium stars. 3 to 5 have been called strong barium stars. And we find that the distributions of these two groups are really similar. This contradicts previous claims, but we don't find a significant difference there. But what we find is that there were, in the catalog of LU 1991, there were some new objects introduced and described as having a barium index smaller than 1. And we find that these objects pollute the higher mass tail, so those are the ones that appear to be at higher masses than we expected. And we think that these objects are not barium stars, just very luminous giants. So we finally also correlate the location of the stars on the HR diagram with their orbital periods, because at the same time we are building an eccentricity period diagram. So we have orbital parameters for a lot of these objects. And this HR diagram is the same one as before, but includes only the objects for which we have orbital parameters. And we separated the sample in two subsamples, one with the main sequence objects or objects before ascending the RGB, and a second sample with objects in the clamp that we expected have gone through the RGB and the RGB tip. And we see a tendency of larger periods here than in the main sequence objects. And yes, you can see it in the histogram. And we think that these objects will never make it through the RGB. And the comparison of these two subsamples can give us help to study the tidal interaction through the RGB phase. So yeah, this is what we have done. I have shown you the HR diagram of barium stars that we have built after the first Gaia data release, and the mass distribution that we have obtained from it. We conclude that we still have important uncertainties, those related to the stellar parameters, but also the choice of the metallicity, which cannot be constrained by an SED. And also, of course, the uncertainties in the evolutionary models that we use to compute the mass distribution. We found that barium stars seem to evolve as normal red giants and accumulate in the same region in the HR diagram. We find that subgiant CH star and dwarf barium stars seem to occupy the same regions, and also that the strong and mild barium stars don't have a different mass distribution. And finally, we found a correlation between the location of these stars on the HR diagram and their orbital period, with a tendency for larger periods in the red clump. So, thank you.